Hello! We introduced cooperative games last time. In cooperative games, the outcome consists of a coalition structure, which is how you divide the players into coalitions, and a payoff vector, which is how you distribute the value of a coalition to its members. Not all the outcomes are desirable, however. We do not want to arbitrarily assign people to groups or assign values to players. So what kind of outcomes are we looking for in a cooperative game? Back in non-cooperative strategic games, the goal is to find a Nash equilibrium. This is the outcome that we expect the players to make, and it is a stable outcome. In cooperative games, the players don't make the choice. An outsider would impose a coalition structure and a payoff vector onto the players. And here are two desirable properties of an outcome in cooperative games. The first one is fairness. This means that the payoff vector should reflect the contribution of the players to their coalitions. The second property is stability. We want to incentivize the players to stay in their assigned coalition in the coalition structure. Now, there are different solution concepts that attempt to achieve these two properties. We will discuss one solution concept that deals with fairness and one that deals with stability. We start with the Shapley values. The Shapley values deal with the fairness of the payoff vector. We will assume that the players form the grand coalition. If it is not a grand coalition, we can look at the individual coalitions separately. And the main question is how to quantify a player's contribution. We start with a simple idea. We will compare the value of the coalition before and after a player joins it. So for example, in the ice cream game, the contribution of A is the value of the grand coalition, ABC, minus the value of BC, and that is 0.5. Doing the same calculations, we get the contribution of B is 1 and the contribution of C is 1. These are the contributions of each player to the grand coalition. And now here is a question. Can a payoff vector take these values? And the answer is no. The problem is the sum of the payoffs may exceed the value of the coalition. X of n is strictly greater than V of n. In our example, the sum total of the contributions is 2.5, but the value of the grand coalition is just 2. And it is impossible to distribute 2 liters of ice cream to the players who want a total of 2.5 liters. So perhaps a way to get around this is to fix a sequence of the players and see their contributions sequentially. Using our example again, suppose we use the sequence A, B, and C. We start with the empty set, and when we add A to it, the value is still 0, so A contributes 0. And now when we add B to it, the value of AB is 1, so B contributes 1. And when we add C to the coalition, the value of ABC is 2, so C contributes 1. We see that this is efficient. The sum total of these contributions is 2, which is equal to the value of the grand coalition. X of n is equal to V of n. But can you see a problem with this approach? The main problem is different orderings of the players will produce different results. There is nothing special about the sequence ABC. We would get different contribution values if we switch to another sequence. So here is Shapley's idea. Shapley suggests that we look at all the possible orderings of the players and average a player's contributions. This will give us a formula for a player's contribution that is fair and has very nice properties. To formally define this, I need to give some notations. A permutation of n has the form sigma, which is sigma 1 to sigma n, where each sigma I is a distinct element of n. Essentially, this is an ordering of the players in a line. The element sigma I is at the ith position of sigma. The set of all permutations of n is denoted S sub n. And here are some definitions. Given a permutation sigma, the marginal contribution of player sigma I is delta sigma of sigma I, which is the value of sigma 1 to sigma I minus value of sigma 1 to sigma I minus 1. So this calculates the contribution of the player in the ith position of the permutation when sigma I joins the coalition of all the players that come before sigma I in the permutation. The Shapley value of a player I is then phi I, which is equal to 1 over n factorial times the sum over all sigma in Sn delta sigma of I. The summation here is the sum of the marginal contributions of I over all possible permutations of the players n. There are n factorial permutations, so the average will take the sum and divide it by n factorial. Back to the ice cream game. There are 3 players A, B, and C, so there are 6 permutations, and they are listed here. We can calculate the marginal contribution of A in each of the 6 permutations. For example, for sigma 4, which is BCA, we calculate V of BCA minus the value of BC. That's because B and C come before A, and we calculate the contribution of A when they join the coalition BC, and that is 0.5. So the Shapley value for A is 5A, which is equal to 1/6 of the sum of these marginal contributions, and that is 1/2. If you calculate the other Shapley values, you get phi B is equal to phi C, which is 3/4. This means that when the 3 players form the grand coalition and get 2 liters of ice cream, a fair way to distribute the ice cream to these players according to Shapley is Alice gets half a liter, and Bob and Carol receive 3/4 of a liter each. Now, calculating Shapley values using only the definition is quite computationally intensive. There is an exponential number of permutations. The good news is, there are ways to simplify this calculation for certain cooperative games, and this can be done by looking at some good properties of Shapley values. We will discuss these properties in the next lecture.